The aim of my talk today is to talk about links between optimal transport theory and density functional theory. So here, basically, this is based on joint work with Aurélien Alfonsi, Raphaël Coyot, Damiano Lombardi, and Luca Nenna. And I'm going to talk about some sparsity results linked to approximation of some density functional theory functionals, linked to this point of view using optimal transport theory. So I would like to acknowledge this work has been funded by the ERC grant of Eric Cancès, Laura Grégory, Yvon Madé, and Jean-Philippe Picmal. So many thanks to them. And here, actually, I didn't know how many people were familiar with optimal transport theory in the room. So I'm going to first give some short crash course about what is optimal transport theory. So sorry for those of you who know this by heart. You can do your email or sleep a little bit during this first part, okay, for those of you who know this by heart. And then I'll skip more about the links between density functional theory and optimal transport. So you can get awake at this part for the experts in optimal transport. And then I will talk about our joint work, about some ways to approximate numerically this kind of optimal transport problems, and the particular sparsity results that you can get with this particular way of approximating the problem. Okay, so let me first begin with some introduction to optimal transport theory. Another motivation for me to give this kind of crash course is that Geneviève Dusson, who will be here in the second workshop, will also talk to some topics related to optimal transport theory for DFT. So I think this might be useful for those of you who will be there in 2 weeks from now, 3 weeks from now. Okay, so optimal transport, originally it was not at all introduced for the quantum chemistry or DFT at all. It was introduced by Gaspard Monge in his memoir sur la théorie des déblais et remblais. So let me first explain what was the problem that he had in mind. So here the question that he was asking is what is the most economical way to take a heap of sand and to put it into some hole. Okay, and what is the mathematical way to formulate the problem, at least the way he formulated the problem at the time, is the following. So imagine that the sand heap is located onto some set denoted here by x, okay, and that the hole occupies the domain which is denoted here by y, and that you've got two functions, non-negative functions. Nu of x is defined on the set x, and it represents the height of the heap of sand at a given point x belonging to this set. And nu of y here represents the depth of the hole. Okay? And what does it mean finding the most economical way in the way that Gaspard Monge formulated it? It's related to a notion of cost. Okay? So he was assuming that the cost of transporting 1 unit mass of sand from a point x to at some point y inside the hole, well, this had a cost, and this cost is denoted by a function defined onto the Cartesian product of the two domains, C of xy. Okay? And of course, it's assumed to be positive. Okay? And here also, it was some kind of assuming that the total volume of the sand was equal to the total volume of the hole, which amounts to having this kind of relationship between mu and nu. Okay? And so the way that Monge formulated this optimal problem, the way of expressing what is the most economical way to transport sand into the hole, is via the following things. He wanted to find the map T between the set X and the set Y, which transports nu onto nu with this minimal cost. So in mathematical terms, a map T which transports mu onto nu, so it's a map defined on X with values in Y, which satisfies the following property for any function f defined on the set y. Okay. In other terms, for those of you who know this formulation, the good way to interpret this is to say that nu, the target measure, so we're representing the hole, is the push forward of mu, the measure which represents the height of the sand, by such a transport map. Okay. And the cost of transporting mass from the sand heap into the hole via this map C is then defined as this function only here, okay, which makes the cost C appearing. And so Monge's problem was, okay, given some mu and nu that can be interpreted as probability measures on the set X and on the set Y, respectively, can I find an optimal map T from X onto Y, which transports mu onto nu, according to the definition I just told you, and which minimizes the associated cost. Okay. The problem is that this kind of way to formulate this kind of optimal transport problem, well, the denominations come from Monge's point of view, it is a nil-pose problem in general, in the sense that if you've got a probability measure mu onto set X and a probability measure nu onto set Y, in general, there may not be an optimal map which transports mu onto nu and which minimizes this kind of cost. Okay. And this is the reason why Kantorovich introduced another formulation of this problem, okay, which is much well posed. And actually, the problem arising in density functional theory I want to talk to you about are more related to the point of view on Kantorovich onto this kind of problems. Okay. And so what was the idea of Kantorovich there? Instead of looking at maps which transport mu onto nu, he rather thought about considering couplings between mu and nu. And what are these couplings? Couplings are probability measures defined onto the Cartesian product of x and y, and which have marginals equal to mu on nu. So mu is a marginal of gamma with respect to the x variable, and nu is a marginal of gamma with respect to the y variable, which reads as follows. Okay? And then what is the link between such couplings and the transport maps of Monge initially? Well, actually, what you can see is that if you've got a map T from a set X to a set Y, you can associate to it some particular coupling, gamma T, which reads under this form here. And then gamma T is indeed a probability measure, so its definitions come from the choice of the map T, okay? And it has indeed marginals mu on nu with respect to X and Y variable respectively, okay? And you can express the cost associated to a map T, which transports mu onto nu, under this following form, as the integral over the Cartesian product of x and y of the cost C with respect to this coupling gamma T associated to T. Okay? And so the idea of Kantorovich was to say, okay, instead of considering maps between mu and nu, which transfers mu onto nu, let us rather consider couplings between mu and nu in this sense, okay, and see if we can define some optimal optimization problems that have better properties than the original Monge problem, okay. So instead of a reformulation of Monge's optimal transport problem using couplings, as I told you, was to find is there a map T which transports mu onto nu, which minimizes this cost here, so the cost of the coupling gamma associated to the map T. Okay, so this is an nil-pose problem. But Kantorovich optimal transport problems consists then in not considering only couplings associated to maps, but general couplings gamma. And so what he's looking after is to some probability measures defined onto the Cartesian products x with y, okay, which have marginal laws mu on nu, and which minimizes this cost here. So here, to make a notation simpler, I just I just denote this cost as the integral of C gamma over the Cartesian product of x and y. Okay? And Kantorovich optimal transport problem is much more well posed than the original Monge-Kantorovich optimal transport problem, in the sense that under some very general assumptions onto the cost C and onto the probability measures mu and nu, you can indeed prove that there exists an optimal probability measure gamma, an optimal coupling, which minimizes this kind of cost. Okay? So a very simple example, for instance, is the case of the quadratic cost. C of xy is just the Euclidean norm of the difference x minus y squared. Okay? And if you look at the infimum over all, this is a set of couplings between mu and nu, of all couplings which minimizes this particular cost among the set of couplings between mu and nu, this gives you the Wasserstein distance between the two probability measures mu and nu. Okay? And actually, the problem arising in density functional theory are related to this Kantorovich point of view. So let me just, and more precisely, here you see that you've got this probability measure, this coupling between two measures mu and nu. It is a probability measures defined on this Cartesian product set, x times y. You can introduce generalization of this Kantorovich optimal transport problem which involves more measures defined on more sets. And then what you're looking after are couplings, which are probability measures defined onto Cartesian products of a larger number of sets than just two. Okay? And these are called multimarginal optimal transport problems. And they read as follows in general. So here consider n an integer greater than 2. N will later play the role of the number of electrons in the system when I am going to draw the link with density functional theory. And let x1 up to xn be some subdomains of R to the d. Okay? If mu1, mu_n are probability measures defined respectively on the set x1 up to xn, and if you're given a cost functional C, which is defined on the Cartesian products of all these sets here, with non-negative values, then the, what's called the multimarginal optimal transport problem in the Cantor-Horowitz form amounts to finding some probability measures gamma defined onto this Cartesian product set, which minimizes the cost integral over this Cartesian product of the cost C against the measure gamma. Okay? And you're looking at some probability measures gamma, which minimizes this cost under the constraint that the if marginal of this probability gamma is equal to mu. So if you integrate the measure gamma over all the sets except the if one, then you get mu I. Okay, yes?
You just, when you say Cartesian product, what is that? Is this a
sorry.
function of many variables? Or?
Sorry, it's if you've got, so you've got this domain, x1 up to xn. x1 times xn is a set of n applets, small x1 up to xn, with x1 belonging to x1 and xn belonging to xn, okay? So it's all the n applets of variables. The first one belongs to x1, blah, blah, blah. The nth one belongs to xn. Okay. Are there other questions? Sir? No? Okay. And actually, problems in density functional theory are related to problems of this form here that I want to tell you about. But they have some additional feature, which is the following one. You will see later in the talk. I'm going to drive you through this. All the sets x1 up to xn will be equal to the same one. Okay, it will be R to the 3. So here I denote it by x. All the probability measures mu1 up to mu_n will be equal to the same guy, which will play the role of the electronic density, rho. And the cost C will be defined onto x to the n. So x to the n then we'll refer to the set of n applex, x1 up to xn, such that all the variables x1 up to xn belongs to x. Okay? And given such a set, such a marginal rho, which will be the electronic density function, and such a cost function, then what's called the symmetric multimarginal optimal transport problem amounts to finding a probability measure defined onto this set, x to the n, okay, which is symmetric in the sense that if you exchange the order of the variables, then the measure remains the same, okay, and which minimizes this cost under the constraint that the marginal of gamma is equal to rho. Marginal of gamma with respect to one variable, and since gamma is assumed to be symmetric, whatever the variable you do not integrate upon, you will always get the same function here. Okay? So I'm going to talk about, so that's the kind of classical symmetric multimarginal optimal transport problems that arise from DFT. And I'm going to show how this kind of optimal transport problem can be used in order to treat some, to have some insight about some density functional theory, some functionals appearing in density functional theory. Okay. So that was for a crash course on optimal transport. Yes?
Can I quickly ask what are the conditions you need on C to actually make this work?
So you need in particular to be a lower semi-continuous, in particular. And this may not be sufficient, but if X is a compact domain, this is sufficient. Yeah?
And if capital N is 2 and your source measure, target measure are equal, then it's a trivial problem. So is it now non-trivial?
It depends on the cost C. If C is an attractive cost, yes.
Okay.
But in the case of DFT, it will be a repulsive cost. And it will not be a trivial solution. So, yeah, absolutely. If C was some kind of generalization of the square, sorry, where did I put it? Of the square distance here, yes, the solution would be trivial. But this will not be the cost which is interesting for DFT. Okay. Are there other questions? No? Okay, so let me now really speak about density functional theory and its link with this kind of optimal transport problems. So let me introduce some notations that are really related to quantum chemistry and density functional theory. So here, n will be the number of electrons we are interested in, okay? Psi of x1, xn will represent some wave functions associated to this set of electrons, okay? And an here is the set of admissible wave functions for the system of electrons with finite kinetic energy. So psi will be a function which will be square integrable, okay? And whose gradient is also square integrable. And in addition, psi is antisymmetric with respect to the permutation of the variables, okay? And the integral of the modulus of psi square is equal to 1. So that's natural. That's the set where the wave function associated to a set of n electrons will belong. And then the celebrated many-body Schrödinger problem, so lots of you know, most of you know about, reads as follows. Assume that your system of n electrons is in the presence of an external potential that I denote here by small v, okay? Then the ground state energy of your system of n electrons in the presence of this external potential v reads as follows. It is the infimum of the energy among all the set of admissible wave functions, okay? And the energy is equal to this quantity, psi hmv psi, where hmv is the Hamiltonian associated to the system. And it reads as follows, okay? It is the sum of some hn0 Hamiltonians that are right here, which is the sum of the kinetic energy operator, plus the sum of the Coulombic interaction between the electrons among themselves, plus the energy associated to this external potential. Okay? And then, for instance, an example of external potential is the one that is generated by m nuclei within a molecule, okay? With positions where the nuclei are located at positions R1 up to Rn, with nuclear charges given by Z1 up to Zn, okay? So then the external potential is given into this form here, okay? So density functional theory, so I'm grateful to Vikram Gavini who gave a nice introduction to it in the tutorial weeks. Amounts to reformulating this problem here, which is a very high dimensional problem, defined onto the set of wave functions, onto a much smaller dimensional problems, only defined onto the set of electronic densities. So here I'm just recalling the celebrated Hohenberg-Kohn theorem that Vikram told about in the tutorial weeks. So here I need to introduce for any psi wave functions belonging to this set of admissible wave functions, the electronic density rho psi associated to psi is given unto by this formula here, okay? And it holds that the ground state energy of your set of n electrons in the presence of the external potential V, you can reformulate it as this minimization problem, okay, defined onto the set of admissible electronic densities, okay? The set of admissible electronic densities is given by this set here, okay? But here what is important is that here what appears here is the sum of two terms. So the first terms, which is linked to the contributions of the external potential, can be simply written under this form here. And you've got also the celebrated Hohenberg-Kohn functional appearing here, so which I denote here by FHK of rho, okay? And this Hohenberg-Kohn functional, it is the infimum of all the set of wave functions, the associated electronic density is equal to rho, of the quantity psi hn0 psi, where hn0 is the Hamiltonian, which only contains the kinetic energy part and the Coulombic energy part of the electrons. Okay. So of course, a lot of density functional theory models. Let's say the golden goal of density functional theory is to try to approximate this kind of functional in order to solve this problem instead of solving the many-body Schrödinger electronic problem instead. And lots of DFT models rely on various ways to approximate this functional, which is not known explicitly, okay, and which is quite complicated. So there are lots of different models. There are there are now models where people try to compute approximations of this functional using machine learning tools as well. But also, not only this Hohenberg-Kohn functional is complicated to approximate and to compute, but in addition, it is a non-convex functional. So that even if you knew it, if God could tell you what is the exact Hohenberg-Kohn functional, solving this kind of minimization problems could yield to some difficulties in practice because of its non-convexity. And actually, this is one of the reasons why Lieb introduced another functional, which is called the Lieb functional, FL of rho, which may be less known than the Hohenberg-Kohn functional, and which is actually a convexification of the Hohenberg-Kohn functional. So in other words, you define this quantity, FL of rho. It will be the infimum over all linear combinations of electronic densities rho I with weights alpha I such that this constraint is satisfied. The sum of alpha I rho I is equal to rho of this quantity here, where here you've got the value of the Hohenberg-Kohn functional evaluated at rho I, which appears here. Okay? So if you define this functional this way, well, you can easily see that it is convex indeed. And it has the interesting property that if you want to express the ground state energy of the electrons within your system, you can also reformulate it as an infimum problem over the set of electronic densities with this Lieb functional instead of the original Hohenberg-Kohn functional. Okay. So this guy is also very complicated to compute, but it has the advantage of being convex, whereas the original Hohenberg-Kohn functional is not convex. Okay. And still, if you solve this kind of problems, you still get the ground state energy of the electrons. Yes?
So I'm just a little bit confused. So I remember the Lieb functional is kind of a Legendre transform of the total energy, where you subtract and you maximize with respect to the potential.
Yeah. So I will give the other formulation of this Lieb functional. This is equivalent. Yeah. Yeah. So there is the other one that is more related to optimal transport theory, indeed. Yeah. Are there other questions? Okay. So indeed, having access, if one could have access to this Lieb functional rather than the Hohenberg-Kohn functional, that would at least, on the level of solving this minimization problem, this would help in the sense that this one is a convex problem, whereas the other original one, this one is not convex. Okay. But of course, you haven't. One hasn't solved the problem of having something that is easily to approximate or to compute at this point. So there is another way to express this Lieb functional, which amounts to introducing another minimization problem similar to this one, except that instead of minimizing this quantity here only as a set of wave functions, the electronic density associated to which is equal to rho, you are going to define a minimization problem which where the energy of this Hamiltonian here is minimized over the set of mixed states, instead of just pure states of this form here. So more precisely, here you are going to consider some operators, which will be denoted by gamma, which acts onto a set of antisymmetric functions which are squared integrable, okay, and which can be diagonalized into this form here, okay. So it will be a convex combination of pure states, okay, in the sense that these guys here are projectors onto the wave function psi, okay. Then, instead of having wave functions, you consider operators here, and that will be the objects you're going to minimize upon, okay. And still to this kind of operators, so that are non-negative trace class operators onto this set here, you can associate corresponding electronic density, rho gamma, and rho gamma of x is then defined as the sum of alpha I, rho psi I of x, where rho psi I is the electronic density associated to these wave functions psi I. Okay, and here what you want on this alpha I, so these psi I are typically orthonormal, okay, and these alpha I are non-negative weights, such that their sum is finite. And then the Lieb functional, you can write it onto this form here, okay? You minimize over this set of operators gamma that are mixed states, okay? The electronic density associated to which is equal to rho, okay? And which minimizes the energy of these mixed states, which writes as the trace of the Hamiltonian operator times gamma. And in other words, this energy then writes as a sum, so if you decompose gamma under this form here, this energy reads as the sum of alpha I times the energy of the wave function psi I. Where here again, the Hamiltonian only involves the kinetic operator and the Coulombic operator associated to interactions of electrons within themselves. Okay. And this actually is related to optimal transport in the sense that it is a generalization of the multi-marginal optimal transport problems that I've introduced to you before, except that instead of considering probability measures, you're optimizing onto these sets of operators that have this particular form. Yes?
Sorry, can I just check that I've understood? Gamma is just a single particle density mechanism, right?
No, because these psi I are n-body electronic wave functions.
Okay, they're n-body.
Yeah, they are n-body. So these are the operators acting on n-body wave functions.
But then gamma is a density, is a many-body density.
Yeah, absolutely. The electronic density then is a one body. Absolutely. And then this, this problem here has a connection with optimal transport problems I've introduced before. It's a generalized way to define an optimal problem, so it's called quantum optimal transport. But I'm just going to relate this quantity and the Hohenberg-Kohn functional with the more classical optimal transport problems I've told you about in the beginning of the talk. Okay, so just remember this form here. I'll come back to it later in the talk. Okay, so actually, the link between density functional theory and classical optimal transport problems can be seen via the strictly correlated electrons approximation of the Hohenberg-Kohn functional. Okay, so let me explain to you what this is about. So here again, Hn0 here, it's the sum of the kinetic operator T here, and the operator associated to the Coulomb potential, which is this guy here. Okay, and you see that C here is chosen purposely. Okay. Now consider a Hohenberg-Kohn functional that would be parametrized by some parameter small h here, where instead of minimizing this quantity here with the full Hamiltonian Hn0, you minimize an analogous quantity, except that the kinetic energy is multiplied by this scalar factor h. Okay, and you can wonder what is the limit of this functional if you neglect the kinetic energy term in comparison to the Coulombic energy term here. Okay, and this leads to the so-called strongly correlated electron limit of the Hohenberg-Kohn functional, which is the limit as this parameter h goes to 0 of this h-dependent Hohenberg-Kohn functional. Okay, so here basically you're looking at what happens to this functional when you neglect the kinetic energy influence of the kinetic energy terms in front of the Coulombic energy terms. Then this quantity, which actually was first considered, so this CE limit was first considered by Seidel and then by Gori, Georgi, and Savin. Okay, and was one way to try to understand what could be a good some approximation of this Hohenberg functional in a strongly correlated limit. And you can relate it to a classical optimal transport problem, the form of which I've introduced to you at the end of the first part of the talk. So the link is the following. If you take psi a wave function, then its modulus squared, it's a symmetric probability measures on R3n, okay? And psi, C psi here, where C again is a Coulombic potential, you can interpret it as the integral of C, which now you can see as a cost function, against the measure gamma psi, okay? And in addition, if gamma is a symmetric probability measures on R3n, then you can relate the electronic density associated to the wave function psi as the marginal of this symmetric probability measures, modulus square, times the factor n, which is the number of electrons here. Okay. So here, actually, this limit, a strongly correlated limit of the Hohenberg functional, it was proved by these people that you can interpret it as an optimal transport problem, a classical optimal transport problem, in the sense that it is given as the infimum over the set of symmetric probability measures on R3n, the marginal of which is equal to the electronic density rho of the integral of the cos C times gamma, where C is a Coulombic potential. So you see here, C indeed is not an attractive cost. So related to your question, this is a repulsive cost. And then even if you look at symmetric probability measures, which have, well, then which has one marginal, whatever the variable you took at it, you don't have a simple solution for this guy. Okay. So here, of course, this classical optimal transport problem only arises when you consider this strongly correlated electron limit of the Hohenberg function. And so whether this kind of approximation of the Hohenberg functional is relevant or not, it depends a lot on the type of systems you're looking at. And in particular, it depends a lot on whether the influence of these kinetic energy terms are important or not. Okay, so just a brief recap on these two links between functionals arising in DFT and the optimal transport problems. So there is this Lieb functional, which is the functional which is the most relevant for quantum chemistry application, which is as this kind of minimization problem, okay, where you minimize over the set of mixed states that are operators acting on n-body wave functions, and with associated density equal to rho, some electronic density. And you've got this classical optimal transport counterpart, which is given by this strongly correlated electron functional, okay, where here the minimization problem is defined over the set of probability measures on R3n. The associated marginal is equal to rho, up to the factor n related to the number of electrons. Okay. But you've got the same kind of structures in the sense that this constraint here is a generalization of this marginal constraint that appears in this classical optimal transport type of problems. And so these two problems, they share some common mathematical structure. And the question is, can we use some kind of techniques imported from optimal transport and which have been more developed for classical optimal transport problems in order to derive some numerical schemes in order to try to approximate this Lieb functional. Okay, that's what we are trying to do at this point. I'm not saying that we have something very efficient at this point, but I can tell you about some preliminary steps which are going towards this direction in the sense that we would like at some point to have some numerical schemes which would try to approximate this Lieb functional, at least for some systems of reasonable size. Okay. And here I'm going to tell you about some approaches that we've developed recently, mostly for this kind of problems which are more classical, okay, but for which there may be some hope to gain some numerical methods which could apply also to this kind of problems. Okay. So let me just tell you very briefly why these kind of problems are difficult to approximate, in particular this one. Okay. So the classical way to obtain some discretization of this kind of optimal transport problem is to approximate the probability measure gamma by a discrete measure. Okay. And more precisely, traditional way of discretizing things is to introduce a discrete grid of R3 here. We have points y1 up to ym, okay, and to approximate an optimal probability measure gamma by a probability measure which will charge all the points belonging to the Cartesian product of this discrete grid, okay, y to the n. So this amounts, so if you fix the points belonging to the discrete grid, this amounts to computing some weights, gamma I1 up to yn, and you've got m to the n weights to identify in order to approximate such a probability measure. So when n, the number of electrons is large, you face the curse of dimensionality. Somehow there's no free lunch. That's the same kind of things that you would tackle if you would approximate the Röhrenberg functional from the start. Okay, and the complexity is even worse if you want to use classical discretization schemes to approximate the Lieb functional as well. Okay, so there have been some works in the mathematical community to try to avoid this curse of dimensionality for the classical optimal transport problem, so for the strongly correlated electron functional. Okay, so here I'm mentioning, well, the list is non-exhaustive, but there are the main methods that have been used to tackle this problem. Okay, in particular, I'm mentioning some works by Gabriel Perret, collaborators, and Luca Nenna about the use of the so-called synchron algorithm. There have been some work by Lieb and Christian Mendel, which use the dual formulation of this problem. Okay, and there are also some recent efforts by Gero Frieseke and members of his group about the algorithms that they call the genitive column generation algorithm, and which uses the fact that actually, if you use this kind of discretization methods, minimizers, associated minimizers have a sparse structure. Okay, so they rely on a discretization of the state space. So they introduce a discretization grid of R3, but they use the fact that actually there are only a few of these weights here that are non-zero to design some algorithm in order to solve this kind of problems. So together with Aurélien, Alfonsi, Raphaël Collio, Damiano Lombardi, we looked at different ways to approximate these problems using moment constraints, okay, that I'm going to tell you about, and which leads also to sparse minimizers. But here, still, we are not discretizing, sorry, without the use of a discrete grid of the state space. And that's the whole point. And actually, this kind of moment constraints, they can lead also to some sparse minimizers when you want to use them to approximate the Lieb function. Okay, so that's why what I'm trying to, will try to explain to you in the next slides. Okay. So I need to introduce you what are these moment constraints, okay, to approximate these two kinds of optimal transport problems. So I need a technical assumptions on rho. With this kind of assumption means that rho has to decay fast enough at infinity. That's but it's kind of a mild decay that is allowed. Okay. And then I have to assume I'm going to introduce some functions, phi m, that are defined over R3. And I have a sequence of those. So this will be denoted by a phi m, and m is an integer. Okay. And this will play the role of these moment functions. I'm going to tell you where the moments come into play in the next slide. I need to assume that the first function is identically equal to 1. This will be to have the charge conservation, or to be satisfied by the solution of the approximate problems. And I also need that if I've got an electronic density, okay, such that the moment of this electronic density rho tilde with respect to this function phi m are equal to the moments of the original electronic density rho that I consider, whatever the moment functions belonging to this family, then necessarily rho tilde has to be equal to rho, the original. So in other words, the electronic density rho has to be fully characterized by this set of moments. Okay. Under some mild assumptions on the electronic density rho and on this function theta, you can derive some simple families, phi m, that have this kind of properties. For instance, finite element functions do have these properties. Okay. So in the following, I'm going to denote by rho m the moment of the electronic density rho with respect to the moment function phi m. It's just the integral of phi m against rho. Okay. Then what you do is that in both this kind of optimal transport problems, the SC1 and the Lieb one, okay, you are going to replace the constraint on the electronic density, okay. So in the SC case, it's a marginal constraint. You ask for rho gamma to be equal to rho. And in the Lieb case, you also ask for the electronic density associated to the operator to be equal to rho. Then these exact constraints, you're going to replace them by a set of finite set scalar constraints where you only impose the moments of these densities here, rho gamma and rho gamma, with respect to the m first moment functions phi m to be equal to those of the original electronic density. Okay. So this full constraint, you only relaxed by this finite number of scalar constraints. Okay. And you have to add an additional technical condition. Okay. This is not very important for what I want to tell you about. And then if you do so, you obtain some approximations of the exact strongly correlated electron functional and the exact Lieb functional. Okay. And of course, these approximations, since the set of measures gamma or operators gamma, which only satisfies these m moment constraints, is larger than the one which satisfies the full density constraints, these quantities are approximations from below of the exact functionals. Okay. And then, well, you can prove that indeed, as the number of test function and of moment constraints goes to infinity, these approximations do converge towards the exact quantities, so that's very natural. But what is more interesting is that in both cases, you can prove that the minimizers of the moment constraint approximations have a sparse structure, which can hopefully be used to design some numerical schemes. So in the strongly correlated electron case, what you can prove is that if you use m moment constraints, you can find a minimizer of your approximate moment constraint problem, which is a measure which only charges, which is a discrete measure, and which only charges a number of points, which is at most equal to the number of constraints plus 1. Okay. And this leads to sparse representations of minimizers of your approximate functional, the complexity of which only scales like m times n, the number of electrons. So just to compare with classical discretization scheme, the complexity was exponential with the number of electrons. And here, instead, it is only linear with the number of electrons. So this is a nice thing about the sparsity of these minimizers, that you can exploit to design some numerical schemes, which could lead to amenable solutions when you've got a large number of electrons. And you've got a similar sparsity results for the Lieb functional, in the sense that you can prove that there are minimizers gamma to the approximate moment constraint Lieb functional, which are only operators, the rank of which is at most equal to m plus 1, using exactly actually the same lines as in the classical case. And so this also yields to some sparse representations of the minimizers of these approximate functionals, which hopefully could yield to some possible numerical schemes in order to approximate the Lieb functional. So we are not at this point here for the Lieb functional. So we are still currently working on some algorithms which exploit this kind of sparsity in the Lieb functional. But I can tell you about some results that we obtained for the strongly correlated electron case. Okay. So if I go back to the strongly correlated electron case, a natural idea is then to say, okay, let's look at the minimization problems that I obtain if I restrict the set of measures on the set of measures that have this particular form. Okay. And I want to minimize the functionals that I get in order to find optimal weights wk and optimal points xk. Yeah. And that this leads to such a kind of a minimization problem. Okay. So the advantage here is that you've got only n times m's quantity to identify. Okay. But there is a price to pay, which is that this guy is a non-convex optimization problem. But in order to solve this guy, so we use some stochastic gradient algorithms, which uses constraint over Dampf-Langevin dynamics, basically, to solve this kind of problem here. So I'm going to show you some results that we are able to obtain with this kind of approach exploiting this sparsity structure. First of all, some numerical results in 1D. So the advantage of 1D numerical results is that you know, in this case, analytically, what is the solution of the exact problem. So you can compare what the numerical scheme gives you with respect to the exact solution of your problem, which you don't have in the 3D, basically. But here are 3 examples of 1D electronic densities, ρ1, ρ2, ρ3, okay, which are more and more oscillating, okay. And these are just some toy numerical tests for 5 electrons, and where you use as moment functions some polynomial test functions, okay. So typically what you observe when you look at the evolution of the cost as a function of the number of iterations of the optimization scheme is that there is some kind of plateau region, and then at some point the cost suddenly decreases. But of course, as the number of moment constraints you impose increases, this decay will happen at a higher number of iterations. Okay, so that's kind of expected. And here is the kind of things that you obtain there. So here ρ1 was a uniform density, okay, to begin with. And here these diagonal red lines, they are, so here what you see, we have 5 electrons. So the probability measure that you're looking at is a probability measure defined onto r to the 5. Okay. So these are plots of 2D marginals of this particular probability measure. Okay. And the red lines corresponds to the support of the exact solution of the exact optimal transport problems. So if you use these moment constraints and these particle schemes, what you obtain is this kind of results, where you see here the blue dots are places where the particles localize when you optimize this quantity here. Okay, sorry. When you optimize the set of this, the location of this particular points, that's what you obtain here. So what you can see, so this stochastic gradient optimization algorithm enables to obtain some optimal locations of these points that are indeed located onto very close to the support of the exact solution, of the exact functional. So these are some results obtained for the other two electronic densities here, and you've got exactly the same kind of observation. Okay. And this is another example. So here for 100 electrons, and when your electronic density is a 3-dimensional function. Okay. So here we took some example where ρ is a sum of 6 quotient functions. Okay. And when you impose 52 moment constraints with some polynomial test functions, and here, unfortunately, you cannot see very well, but these are various 2D plots of these probability measures that you compute with this particle scheme. So here, the measure that we are looking for, it's a measure defined over r to the 300, okay? And this has various 2D slices of this of the measures that you compute with this particle scheme. And the thing that is nice here is that since you've got only a complexity which scales linearly with the number of electrons, so this helps a lot in having some results for a high number of electrons. So here 100 typically. So just some conclusions. So here what we have the line of research that we have tried to explore is to consider alternative ways to the most classical ways to describe these optimal transport problems using moment constraints. And the advantage of this is that they yield to sparse minimizers. Okay. So in the case of the classical optimal transport problems, so which is reads as a strongly correlated electron functional, we could use this sparsity properties of the minimizers to design some numerical scheme which scales quite nicely with the number of electrons in the system. Okay. So, and it yields some encouraging numerical results. So what we would like to do would be to try to extend these ideas in order to design also numerical schemes for the Lieb functional, also exploiting the sparsity structures of these approximate problems that I've told you about. So this is still work in progress with Luca Nenna. One thing that we would like to do would be to find a more efficient numerical scheme which would allow for more moment functions. At this point, we are not really, the problem does not come from the number of electrons, at least on the classical optimal transport case. It really comes from the number of moment functions that you use to approximate the density. Here, the scheme really struggles when you go higher than this kind of moment functions. So it would be nice to find some kind of schemes which would allow to have more moment functions, to have more accurate approximations. And this yields to the questions on how to choose these moment functions so that it yields some as accurate as possible approximations of the exact functional you want to approximate. What would be nice would be to have some kind of proof of convergence of this numerical scheme. So there are very interesting work of Gero Frieseke and his collaborators in these directions for the GenCall algorithm. That they obtain, they are able to prove that this algorithm converges for 2 electrons, but it's already a start, okay, for this kind of problems. And it's more than we are able to achieve for now. And perhaps a kind of a very open question, very long-term question. If one was able to find some scheme in order to approximate this Lieb functional, would it make sense to try to learn this Lieb functional instead of the original Weinberg functional? So it's kind of the long-term goal of this work, in the sense that if one approximates this Lieb functional instead of the Weinberg functional, you still can have access to the ground state energy of your electrons. But here, the problems that you have to solve are convex instead of the more traditional, let's say, optimization problems that one look at when considering density functional theory. Okay, so with this, I'm done, and I thank you for your attention.